Do you guys remember last week when we played the Starburst game? The rules for the Starburst game, just as a reminder. I handed you a bag that had how many Starburst in it? 6. What was the color distribution inside the bag? 4 red, 2 yellow. And how did you win the game?
By getting a match.
By getting a match. 2 reds or 2 yellows. After you reached in the bag and grabbed the first Starburst, you looked at the color and then did what? Wrote it down and then put it back in. So you always had, before you reached into the bag, you always had 6 Starburst in the bag. Are the events first is red and second is red independent in the game that we played last week? Yes. Why? The probability didn't change. Yes, we were doing this with replacement. No matter what happened on your first draw, the probability for the second draw was exactly the same. If you got a red Starburst on your first draw, it was still a 4 out of 6 chance of getting red on the second. If you got yellow on the first draw, it was still 4 out of 6 chance of getting red on the second. We had the same probability no matter what. Right here on number 2, what I have highlighted, I would circle that or highlight that or do something so that this stands out to you. This is hugely important, and why it's not bold and much bigger on the page is beyond me. For independent events, if you want the probability of the intersection, the probability of both events happening, the and, you take the probability of event A and you multiply it by the probability of event B. This is only for independent events. So we said with the way we played the game last week, these were independent because my probabilities don't change no matter what happened on the first draw. So how would I calculate the probability that the first Starburst is red and the second Starburst is red? 4 out of 6 times 4 out of 6. So that gives us 16 out of 36. If you need a reminder for why we can do this, if you look back at page 7, which is where we did the Starburst activity last week, you can see we wrote out the entire sample space. You can count all 16 ways that we can get 2 reds. What's the probability that the first one you draw is yellow and the second one is also yellow? Be 2 out of 6 times 2 out of 6 for a total of 4 out of 36. So this is how you win with 2 reds. This is how you win with 2 yellows. So what's the probability that you just won? 20 out of 36, which is 0.556. Why am I allowed to just add these together and not worry about subtracting anything back out? There's no way to win by getting 2 reds and at the exact same time on the same turn win by getting 2 yellows. There's nothing in that intersection. These are mutually exclusive events. If you won this way, you didn't win this way. And if you won this way, you didn't win this way. So I can just add them together. I don't have to worry about subtracting back out. We're going to play the game from last week again. I'm going to pass the bags back out. I'm going to partner you guys up. But this time there's a little bit of change to the rules. This time, you will not replace the first Starburst before getting the second one out. So you're going to reach into the bag that has 6 Starbursts. You're going to pull one out. You're going to set it on your desk. Then you'll shake the bag up and reach in again. How many Starbursts are left in the bag when you reach in the second time? 5. You're going to pick one of those Starbursts out. You'll set it on your desk. If they match, you win. If they don't match, you don't win. All right? You and your partner are going to play 10 games. You'll each play 5 games. And I want you to keep track of how many wins there are in your whole group. So out of 10, how many times do you win? I'm going to partner you guys up, just like we did last time. you two together. Jim and partner Colin. I'm going to partner you two together. I'm going to partner you two together. Georgia. Partner you two together.
Wait, who's Simone?
Simone is with Hayden. Partner you two together. 10 games total. Keep track of how many wins each person plays 5 games. Just keep track of how many wins your group has out of 10 total games.
Are we going in or no? Never bet on it. Do you feel a little rock?
Yeah, they're very good. They're like 4 years old. Don't eat them.
What's the probability? What about my diary?
Probably the dying is pretty low. Probably breaking a tooth is much higher. You only got 1 win in 10 games? You? How many wins do you guys have? 6. How many wins did you guys have? 5. How many wins?
Oh, did y'all sing in the hallway? He's probably singing. Oh my God.
I kid you not, there was no headphones in this ear. Neither side.
Yo, what? All right, question. We have 16 people in the room today. How many games got played around the room? We have 16 people in the room. How many games were played? How many?
How many games were played?
How many games were played? 80. Yes. Because every group, every pair of people played 10 games. Every person played 5 games. All right, so we had 80 games total played in the room. And I came around and got your number. We had 38 wins out of 80 games. What is 38 divided by 80? How much?
Oh, no, that's not right. I didn't type in the 3.
0.475 or 47.5%. What is that 47.5%? Like, what did we just calculate?
The win rate.
The chance to win, is that the true overall probability chance of winning? No, that was the chance of winning in this room with those particular games. So that would be my estimated probability of winning, because we just used simulation. We just used simulation to try to approach the true probability. We are going to use something called a tree diagram to calculate the true probability of winning the game. So in a tree diagram, the first thing we're going to look at is we have a split, because two possible things happen when you reach into the bag. You either reach into the bag and you grab a red, or you reach into the bag and you grab a yellow. What's the probability you got red when you first reached into the bag? 4 out of 6. The probability that it was yellow the first time? 2 out of 6. And now we get into some conditional probabilities. Given that the first one was red, so I'm following this path here. The first one was already red, so this is my given that. What's the probability that the second one was also red? 3 out of 5. We had 5 left in the bag. We took one of the red ones out here, so there were 3 left out of the 5 total. So to find the probability that the first one is red and the second one is red, do you guys remember back when I said for independent events, we multiply the probability of A times the probability of B? Well, it's very similar for this, except this is not the probability of event B. This is the probability of event B given that event A already happened. So I'm going to take the probability of event A, I'm going to multiply it by the probability of event B given that event A happened, and that will give me my probability for my intersection, my AND. So I'm going to take 4 out of 6 times 3 out of 5. What is 4 out of 6 times 3 out of 5? 12 out of 30. I'm going to give you guys, take about a minute, minute and a half. I want you to fill in these 3 probabilities here and calculate these 3 intersections here. The probability that the first is red and the second is yellow.
Wait, we should reduce that.
Typically, we don't reduce fractions when we're doing probabilities because that numerator has meaning and the denominator has meaning. Now, if you do reduce the fraction, it won't be counted wrong. There's nothing incorrect about it, but typically with probabilities, we don't reduce our fractions down. So like I said, take about a minute and a half. Finish filling in the 3 probabilities that are on the branches and calculate the 3 intersections. What is this conditional probability right here? If the first one was red, what's the chance the second one was yellow? 2 out of 5. And so the probability that the first one was red and the second one was yellow comes out to be what? 8 out of 30, yes. 8 out of 30. What is this conditional probability? Given that the first one was yellow, what's the probability the second one is red? 4 out of 5. So what's the probability that the first one was yellow and the second one was red? 8 out of 30. And what is this conditional probability? Given that the first one was yellow, what's the probability the second is yellow? 1 out of 5. So the probability for the intersection, the first is yellow and the second is yellow? 2 out of 30. Now, something I want you guys to notice, the ends of these branches, these probabilities here, 12 out of 30, 8 out of 30, 8 out of 30, and 2 out of 30. These events, first is red and second is red. First is red, second is yellow. First is yellow, second is red. First is yellow, second is yellow. That's all the possible things that can happen in this game. These are all mutually exclusive. This can't happen at the same time this happens. These are all mutually exclusive. I want you to add those 4 up. What happens when you add those 4 probabilities together? You get 30 out of 30, or 100%. It is a 100% probability that one of these 4 outcomes happens. And so the general rule for how we find an intersection, an and, is we take the probability of our first event, and then we multiply it by the conditional probability. We multiply it by the second is red given the first is red. So you take the probability of the first event times the conditional probability for the second event. This right here is how we calculate the and. For independent events, I just do probability of first red times probability of second red. When they're not independent, this has to be a conditional probability. So how would I calculate the probability of winning this game? Which outcomes would represent winning? Red and red, yellow and yellow. Those would be winning. And these are mutually exclusive, so to find the probability of this or this, I can just add them together. So what's the probability of winning this version of the game? 14 out of 30. What is 14 out of 30 as a decimal? What is 14 out of 30 as a decimal? What is 14 out of 30 as a decimal? Grab your calculator if you need to. Cell phone calculator's fine. 0.47. Yep, 0.467, so about 0.47. What was our estimated probability of winning just from the way things turned out in the class? 0.47. We got really close to the true theoretical probability. We estimated 0.475, and the true theoretical probability is 0.467. What is the probability that the first candy was red, given that the person won the game? So first of all, let's talk about notation. Notation is important because that tells me how to set things up. The probability that the first candy was red looks like this. What's the symbol for given that? Vertical line. So the probability that the first is red, given that what? Given W, or given that they won. Friday we learned the formula for this. How do we calculate a conditional probability? I know it's going to be a fraction. It's what over what, and I'm looking for symbolic, not numbers right now. What goes up in the numerator when we want to calculate a conditional probability? Have probability of the intersection of the two events. So the probability of red and win over what? Yes, over the probability of win, over the probability of my condition. What was the probability that the first is red and you win? 12 out of 30. What's the probability of just winning? 14 out of 30. So I have 12 out of 30 over 14 out of 30. I have a fraction on top of a fraction. Notice my denominators on both of these match, so they cancel out. So that would give me 12 out of 14. And win. So the first one drawn was red, and they were a winner of the game.
86%.
Yes, about 86%, 0.857.
Wait, is the and the upside down U?
And is the upside down U, yes.
But
All right.
There's more red than
Down at the very bottom of your page or in a side margin somewhere, I want you to find a little bit of room. It can even be at the top of the next page if you want. But I want to find room to write this down. I wrote it kind of big. You don't have to write it as big. But here's what I want. This right here, what I wrote in black, that's this. If I want the probability of my numerator, if I don't have a two-way table to look at, or I don't have a tree diagram to look at, if I want this probability, you multiply by your denominator. So to find the probability of the intersection, I take the probability of my event. In this case, we're going to call this event A, and we multiply it by the probability of B given A. If you want the probability of the intersection, you can take the probability of your condition times the probability of event B given your condition. Using some basic algebra here. On the formula sheet that you get to use on the test that's coming up on Friday, as well as on the AP exam in May, you get this formula right here. It says the probability of A given B is equal to the probability of A and B over the probability of B. You have that formula for reference on that formula sheet. The other formula that you get from this chapter that will be on the formula sheet is the general addition rule. The union is equal to event A plus event B minus the and, minus the intersection. Let's look at page 16. Page 16, up at the top of the page. So up at the top of the page, a couple important things. This is our general multiplication rule. To find the and, to find the intersection, you do event A times event B given A. If the events are independent, then the probability of B given A is just the same as the probability of B. If the events are independent, then whether or not A happens doesn't change my probability for event B. So that's how I get this simplified formula for independent events. If they're not independent, then I have to have the conditional probability If they are independent, then I just need the probability of A and B. Tree diagrams, I kind of don't like how they wrote this, so we're going to change something on here. This is event A complement. This is event B given A. Down here would be the probability of B complement given A. Instead of doing C given A, this is like, here's event B, it rains. This is, it doesn't rain. Down here, probability of B given A complement. Probability of B complement given A complement. I just don't like the way they wrote that. And then this little asterisk down at the bottom seems like a little footnote. This is super powerful and super important. If I want to know the probability that something happens at least once, I do 1 or 100% minus the probability that it never happens. The probability that something happens at least once is 1 minus the probability that it never happens. Because there's only one way for this to happen. So I just have to do a subtraction for this. There's one thing to calculate here. If I wanted to calculate this directly, I would have to look at all the possible ways. So the first thing happened, but then it didn't happen here, here, here. Or it didn't happen, then it did, then it didn't. Or it didn't, did. Like, there's way too many ways to go about this. But there's only one way for it to never happen. So I can calculate this much more efficiently by doing 100%, 1 minus the probability that it doesn't occur. Check your understanding. The first thing I want you guys to do on this check your understanding is to read through this here and to draw a tree diagram that goes with this description. I'm going to give you guys 2 minutes. I want you to stop when you're done with the tree diagram because I want to make sure that we have the correct tree diagram before we go on and do numbers 2, 3, and 4. So take about 2 minutes to draw your tree diagram. You're starting to get it set up. You stuck?
The boxes.
You've got the correct like basic layout for it, which is not unuseful. So I want to think about this for just a second. We've got people showing up to urgent care to take a flu test. Why do you think they're showing up to take a flu test? Because they think they have the flu. So they're probably showing symptoms, right? So which thing comes first? You get tested or you get sick?
You get sick.
You get sick. So the first thing that we would be looking at is, do you have the flu or do you not have the flu? Because that would happen first. We don't know whether they have the flu or not, but that's the first thing that has actually occurred. What's the chance that a patient has the flu? 22%. So what's the probability that they don't have the flu? 78%, yes. All right. So 0.22 that they have the flu. You can either write these as decimals or percents. It does not matter. However, if you write them as percents, when you multiply them together, you're going to have to calculate that correctly with your decimal places. Patient does not have the flu is 0.78. Given that the patient has the flu, so we're on this branch up here, what's the chance they test negative? 3.7, so 0.037. So if they really do have the flu, they're going to get a false negative 3.7% of the time. So what's the probability that if the patient has the flu, they get a positive test result back? Point what? 0.963. Yes, 0.963. Because these two add up to what? Adds up to 1 or 100%. 3.7% chance of this means a 96.3% chance of this. Given that the patient doesn't have the flu, what's the probability that they got a positive? Yes, 0.026. So what's the probability that if they don't have the flu, it came back negative? Yes, 0.974. So then we can calculate our intersections. Up here is the probability that the patient has the flu and tested positive. How would I calculate the probability that the patient has the flu and tested positive? So this is positive given flu. How do I calculate the and, the intersection? Multiply. We're going to take 0.22. We're going to multiply it by 0.963. And that would give us 0.21186. What is this the probability of again? This is not a given that. This is an and. This is my given that. This is my given that. This is the probability that of the whole population, I randomly pick a person out, that person has the flu and tested positive for the flu. So a randomly selected person has the flu and also tested positive. That's what this is. So how would I find the probability that they have the flu but they tested negative? Yep, 0.22 times 0.037, we get 0.00814. Probability that they don't have the flu and still tested positive for it. How do we calculate that? Yes, 0.78 times 0.026, we get 0.020. And then the probability they don't have the flu and they tested negative. Yep, 0.78 times 0.974, we get 0.75972. If I add up these 4 numbers here, we get 1. Because one of these 4 things has to happen. So how would we calculate the probability that they ask for in number 2? Just the probability that any randomly selected patient tested positive. Yes. This one has a positive test result. This one also has a positive test result. They are mutually exclusive. And so we add these 2 up, the 2 highlighted ones. What do I get when I add those 2 together? What do I get when I add my has the flu and positive, doesn't have the flu and positive? Yes. We get 0.23214. That is positive given flu complement. That gives me the probability that it is positive. Number 3, if we select 4 patients at random, what is the probability that at least one of them gets a positive result? So the probability of at least 1 is 1 minus the probability of none. In this case, what do we mean by none? Yeah, not getting a positive. So what's the probability of getting a negative? If the probability of a positive was 0.23214, what's the probability of getting a negative? What's the probability of getting a negative?
0.76786.
Yes, 0.76786. 1 minus the probability of a positive. Or you could add the 2 outcomes that have negatives. This right here is the probability of 1 person getting a negative test result. How many people are we talking about here? 4. Well, what would I do to take it from the probability for 1 person having a negative to the probability of 4 people having a negative? So first negative and second negative and third negative and fourth negative. I heard somebody say it. Not going to multiply by 4, but you're on the right path. We are going to multiply, but we will multiply it by itself 4 times. The probability of a negative times the probability of a negative times the probability of a negative times the probability of a negative. So I would have 1 minus 0.76786 to the 4th power. Yes. The exponent is 4 because it's 4 people. So what we're doing with this right here is we're actually looking at the intersection of these 4 events. First person has a negative, and the second person has a negative, and the third person has a negative, and the fourth person has a negative. So the probability of the first is this, times the probability of this again for the second person, times the probability of this again for the third person, times the probability of this again for the fourth person. We get, yep, yes, right about 0.65, yes. Now, do I typically make you guys go out to 5 decimal places? No, 3 is usually sufficient. If you go out 3 decimal places, that's fine. Last one, number 4. Given that a randomly selected patient is a positive result, How likely is it that they actually have the flu? So this is a given that. Let's talk about notation. The probability of the flu, given that they are positive. The probability of the flu, given that they are positive. I'm going to have a fraction here. Talking about notation now, I don't want a number. What goes up in the numerator? For a given that, what goes up in the numerator? Yes, the probability of flu and positive. What goes in my denominator? Yes, probability of positive. According to our tree diagram, what's the probability that somebody has the flu and is positive? 0.21186. What's the probability that we calculated that somebody is just positive, full stop? 0.23214. So we're going to divide those two, and that will give us the probability that somebody really does have the flu, given that they tested positive. Or if you tested positive, here's the probability that you're actually sick with the flu in particular. And if you divide those, we get 0.91264. So if you tested positive, it's pretty likely that you actually have the flu. If you tested positive, there's a chance you're sick with something else. Right about a 9% chance you're actually sick with something else. But with about 91% accuracy, if you tested positive on a flu test, you're sick because you have the flu. Homework is due tomorrow. Please practice with the tree diagrams. These are incredibly powerful tools for calculating especially conditional probabilities. You can do it for independent events also, but they are especially powerful for conditional probabilities.